percent performance, and the output is in pounds per minute. This is a sample sign response of 0.2 hertz. Delta C is a range of the output, and delta M is a range of the input. These ranges are used to find the amplitude ratios, and the ratio of little t to big T is used to find the phase angle. This is a sample Bode plot of amplitude ratio versus frequency. At this point right here, which goes down to 180 degrees, the KCU was found to be 5% per pound per minute. That line goes down to this point right here in red, and the ultimate frequency was found to be 0.6 hertz, which is 0.6 cycles per second, and we find that by taking 180 degrees and drawing it to that. 180 degrees is when the sine wave is exactly out of shift. So this is our data from what Jimbo was talking about. Our average K gain was 0.6 pounds per minute per percent. Our average dead time was 0.8 seconds. Our tau average was 1 second. Our frequency ultimate average was 0.6 hertz. And our average KCU was 5.4% per pound per minute. And that's a table of what I just said. So continuing with the transfer function, now that we have our values of gain and dead time and tau, we can now build our controller, and this involves using the closed loop transfer function. So based on this equation, we can construct a root locus plot, and from this root locus plot, we can find our values of Kc. We're interested in this range right here. We're interested in the ultimate Kc, the critical damping. We're interested in the 1/500th decay, which is found at 45 degrees. We're interested at 1/10th Kc, which is found at 70 degrees. We're interested in the quarter decay, which is found at 78 degrees. So this is a sample root locus plot. The Kc ultimate was found to be 2.7% per pound per minute. The quarter decay was found to be 1.7% per pound per minute. The Kc 10th decay was found to be 1.3% per pound per minute, and the 500th decay was found to be 0.9% per pound per minute, and the critical decay was 0.66% per pound per minute. These are our results from our regions. As you can see, as the upper range had a higher Kc value because it was our system was running at higher pump performances. This is our proportional controller. Obviously, you can tell that this is the ultimate Kc response because it does not settle down. For this region, the Kc was 3% per pound per minute with an overshoot of 100%. It never settles down, and obviously there's no offset. This is a quarter decay response with a Kc of 1.7% per pound per minute with an overshoot of 33%, a settling time of 1 second, and an offset of 0.5 pounds per minute. This is a proportional controller of 1/10th decay response, the Kc of 1.3% per pound per minute with an overshoot of 20%, a settling time of 1 second, which you can see right here, it's 1 second, and the offset of 0.7 pounds per minute, which you can see from right there. This is a 500th decay response. The Kc was 0.9% per pound per minute. The settling time was 0.5 seconds with an offset of 1 pound per minute. This is the critically damped response with a Kc value of 0.7% per pound per minute. This agrees with what we saw earlier of a Kc value of 0.66% per pound per minute. This is obviously monotonic with a settling time of 0.4 seconds and an offset of 2 pounds per minute. And if we ran some experiments, this is the critical decay of the. We use the critical decay Kc. You can see how it cleanly goes up through there. It doesn't oscillate very much, so we determined that this was the critical decay of the experiment. This is the corner decay of the experiment. You can't really tell, but this is approximately 25% decrease in the height of the output. And this obviously is the ultimate Kc because it's all over the place and it does not settle down anywhere. So next I'm going to pass it on to Jimbo, who's going to continue talking about the PI controllers.